right, so you all know that tomorrow night is the exam, and you know, just go to the same locations as you did last time. Everything is all the same here. I just want to show you that there have been a few corrections on the study guide here, so I updated them, so you might want to check that out again and make sure, some of you might have noticed this already, but if you haven't, just check it out again. And do the other thing that I really strongly recommend that you do are these exam 2 practice problems on ln kappa. So what are we going to do today? So what we're going to do today is just finish up 2 pages in the notebook, and then we're going to spend the rest of the hour reviewing for the exam. So we'll go over some of these problems and some of these problems. All right, so let's go to the document camera, and we left off here on page 178, and we were looking at building this model to predict how well people do on finals given their exams and their homework. And we found that both the homework and the exam slopes were significant in the regression equation predicting the final. All right, so now we're wondering if adding a third predictor variable, third x, would significantly improve our model. So I added, this is from data from a while ago where we used to have computer labs. So I add labs as a third x variable. And now, how do you think, just common sense, well, using common sense, how do you think it would change r squared? Remember what r is. It's a measure of how close our predictions come to the actual finals. You know, the better, of course, we want, the better r squared is, the better our model, right? So if you add a variable, don't you add more information? You either add no information if it's completely uncorrelated with finals, like if I added your weight or something, how's that going to predict your final? But if I add something that has to do with the course, like labs, it probably is going to make a better prediction, right? More information. Well, so r squared either has to go up or stay the same, even if it's negatively correlated. As long as it's correlated, it will go up because it gives you more information. All right, that doesn't mean you have a better model because it comes at a cost. You don't want to make the model too complicated. We'll see that. It costs you what's called a degree. It costs you, if you added lots and lots of predictors, I could perfectly predict all of your finals. I could just add a variable for each one of you. So what I end up doing is fitting our particular sample and maybe not the whole population. So the r squared will certainly go up in our sample, but that doesn't mean that it's going to be a better predictor. So what's our answer? R squared may go up or down. It can never go down. Even if it's negatively correlated, that still gives you more information, and r squared will go up. The only way it would stay the same, it has to go up or stay the same. So if our third variable, x sub 3, if that is correlated with y, negatively or positively, with y, what we're trying to predict, in this case finals, we improve our predictions. We get closer to what the actual y's were in that particular sample. So r squared goes up because it's how close our predictions are to our particular sample. Now, if if x3 has nothing to do with finals like weight or something like that, that's not going to make any difference. If x cubed, if x, the third variable, is uncorrelated, r is equal to 0 is uncorrelated with what we're trying to predict, finals, with y, then r squared, what's this mean? R squared goes up. What's that 0? Sorry, r squared goes up. But if it's uncorrelated, r squared stays the same. Okay? All right, so now, so that's important. And so I checked R squared and saw it went up, but just a tiny bit. Look at this, just from 0.34, just went up in the fourth digit. Look at that, just by 1 there. That's tiny. Okay? Does that mean that adding labs significantly improves my model? Let's look at that. So here we had P equals, all right, what do we have? We have this is a good review right here, just to see that we have a beta naught, a beta 1, and a beta 2. So that's 3 parameters. And now here, what do we have? We have the beta naught, beta 1, beta 2, and beta 3. We have 4 parameters. Okay, so we have 4. This is P equals 3, and here P equals 4. All right, so what changed here? Let's look at what happened. Homework that was significant right here, 1.36, and exams were both significant. Well, homework and labs, these two, are not significant. Their p-values are not under 5%. So they're not significant, these two. All right. Now, where's the R squared that went up? It did go up a little bit. It went up a tiny bit. What else? What happened to our F statistic? Our F statistic went down. You see? So we're going to get less significance. Look at that. R squared went up. R squared went up, but F went down. Do you know why? Why? It's hard. Why? Remember what F is. F is going to be R squared over 1 minus R squared. So that's going to be there's R squared, 0.3841 over 1 minus that, which is 0.6159. And then what do you multiply it by? Do you remember? This is what you should all know. You multiply it by, for chi-squared is just n. But here it's n, that little bit of tweaked n, and here you can see it. N minus what? The number of parameters. So where is n in this? There's 100, I should write that down. N is equal to 107, and the number of parameters is equal to 3. So that's where that 104 comes from. 104 over 2, right? That's n minus p over p minus 1. And when I did that, that's where you get this F statistic. Okay? So even though the R squared went up a little bit here, look why you get a much lower F statistic. Here, this part, hardly 0.3842. Okay, so you're going to get a tiny bit bigger right here. That's going to make it a tiny bit bigger. But look what happens when you add another parameter. Yeah.
A couple of questions. So first of all, you said those two boxes are not significant. Why aren't they significant?
Okay, so the question was, these are significant here, but these are not significant, because remember, we're doing it, to be significant, you have to have, if you're testing it at 5%, these numbers, that's 1.36, these p-values are less than 5%, and these are greater than 5%. 8.47 and 4. Okay?
And then you said p equals 4?
That's the number of parameters, not the p-value.
Okay, then later on you said p equals 3.
P equals 3 here because we have 3 parameters, the intercept, beta 0, beta 1, and beta 2. And P, when we add the labs, see what we did? We added labs here. Okay? Does this mean adding labs significantly improves my model? The answer is going to be no. And that's what we're investigating here, that adding labs, even though we need the R squared go up a tiny bit, let's highlight this, just a tiny bit, it made our model is not significant. I mean, you'll see our F statistic right here. Our F statistic, this is what we're looking at now. This one and this one went down, so we're going to get much less significance here. But why? This part improved it a tiny bit, but we have to look what happens when you multiply by, now you're going to do n minus p, so that's p is 4, so you have 103 over p minus 1. Do you see, this doesn't, it's this 3. Every time you add versus a 2, this makes it go way down. Okay? So what people say is every time you add a new predictor variable, it makes your model more complicated, and it costs you a degree of freedom. That's what it does. It costs you a degree of freedom here. You're going from 2 to 3. Because every time, think about it, if you have more parameters than you have points, you can, well, if you have the same number of parameters as you have points, you can perfectly predict the model. You know, it's like having the same number of variables. You can perfectly predict it, but that doesn't mean that it tells you gives you any information about the next sample you take from that population. You're just fitting that particular sample. So this is worse. All right. R squared did not improve enough to warrant adding the third variable, labs. Labs is not significant, as you can see. But why did adding labs make homework change from being significant to being not significant? Why did it do that? Could this be a mild case of our left foot, right foot syndrome? Remember, you don't want to put two variables into a model that are highly correlated because they're predicting pretty much the same thing. Okay? So let's see. Let's check the correlation matrix. So what do we want to check? We want to check the correlation between homework and labs. Where is that? Homework and labs. You could look at either one of those, and they're pretty highly correlated, very highly correlated. So this means that both slopes can become insignificant when both are included in the model, even though individually both are significant. If you just had homework predicting finals and labs predicting final, they're both significant. We'll see that on the next page. But this does not mean we should throw them both out of the model. All it means is that we can't do a good job of estimating how much of the prediction should be based on one or the other, since they're both predicting the same thing. Remember we said left foot and right foot predicting. Left foot's a great predictor of your height, and so is your right foot, but if you put them both in the model, they could both end up insignificant. That doesn't mean you want to throw them both out. It just means that they don't know. It's hard to tell pretty much any linear combination of the two of them is going to work equally well. So weird things happen. That's called multicollinearity, and don't put two variables in that are highly correlated. All right, so let's see, let's look at this. You'll see this, if you ever take courses like 420 or any kind of applied stats where you're going to be doing a lot of model building, and you'll see this come up all the time. You have to choose which variables you want to put in your model. Okay, so here are the labs. Okay, what's the conclusion? Don't drop them both out of the model. Okay, so here's the homework. All right, so now we have 3 parameters for each now, right? Here's 3 and 3. So now we can compare R squared because we're comparing the same number of parameters. So now when we look at R squared, the one that has the better R squared is going to be the better model because they have the same number of parameters. So, which R squared is higher? Homework. Okay. Also, let's look at the F. Which F is higher? Homework, right? So conclusion. Homework model is better. When comparing, so when you're comparing models with the same number of parameters, like we are here, 3 and 3, then higher R squared also means higher F, right? It's going to mean higher F, and it's going to mean the better model. Okay, look at the SD plus errors above on the right. That's right here. Let's highlight it. Or the SD errors, where are they? Right here. Below for predicting finals for exams. How is it related to 1 minus R squared? We've been talking about this a lot, remember? So the SD errors are equal to the square root of 1 minus R squared times the standard deviation of the y's. And what's the SD plus errors? They're just going to be equal to the standard deviation of the errors times the square root of n over n minus p. You're just going to do that adjustment here. Okay, so they're just bigger, slightly. All right, I think that's pretty much it. And let's just see what we have in the summary, and then we'll be done. I guess we do, okay. We do T or Z test, okay. Question? Okay, so we do the T or Z on the individual slopes after we found the overall. If we see that F or chi-squared, the overall regression, this is on page 180. Yeah, okay. If we see that we've got significance there, then we look at the individual slopes and we do T or Z tests, just like we did before, all right? But you'll be given, we're not going to, the R's and the SDs, they're too hard to figure out, so they'll be given to you here, okay? You're not going to have to, you can't use that formula that you do for the simple slopes, R times SDY over SDX, because remember those R's and and standard deviations change when you have multiple regression. They adjust for the other variables. So you can't use that anymore. For example, you can't use, where is it, in the study guide, you can't use this. This is just for simple regression when you have one slope. We'll go over that in a minute, okay? But you use, you just do the Z and T. They both equal to the observed slope minus your expected slope, which is 0, over the standard error for the slope, or the standard error plus for the slope, and that's given to you. All this is given to you, all right, like it was there. Now, the T and Z tests look the same as in simple regression, but that's true in simple regression, but in simple regression, it simplifies to this really easy formula we can use. Here it doesn't. Okay, now, but the thing that changes, you have to change the degrees of freedom. So this is all you have to remember. The degrees of freedom for the t-test is n minus p, right? In simple regression, that's n minus 2. But if every time you add a slope, that makes the parameters, you'll get n minus 3 if you're fitting a plane instead of a line. N minus 4 if you have 4 parameters, etc. All right. Okay. So we just went over that. Now let's just go over, I think we're done, and we'll start this after the exam. By the way, there's no class, on Thursday. So now let's look at our study guide for just a minute. And let's see, we're just going to go over a few problems in the study guide, and then we'll go over some problems in the practice problem. But first, before we do, let's look at what's going to be given to you. Okay, so this is given to you. It's also the root mean square error. And this is given to you right here. And let's see. What else do you need to know? You definitely, okay, and you need to, if you have SE plus here, for a simple slope, you're just going to change that square root of n to n minus 2, because there's 2 parameters. We'll get to that in a minute. But now here's the formulas that you absolutely need to know. Please remember this. A slope is like rise over run, s dy over s dx, and it's r times s dy over s dx. This is for, you just use this for simple regression. One slope, a line. And here's your correlation coefficient. This is, again, for a line. This is both for lines. And this is all for simple regression for a line. Now, you need to know this, but, you know, if you forgot it, you could easily get it from here. You could just simplify that, right? You could say this is, okay, how does, so you could take, let's say you forgot that. You could say z equals your observed slope minus your expected slope, like you always do, over the standard error for the slope. You know that's true. Observed minus expected over standard error for z-score. Expected 0 under the null, so you've got that. And now you could just use, if you remember this, you'd just say that's r times s dy over s dx over, and then you just plug that, take that, which is going to be on your exam, and put it in the denominator and simplify. So you'd get the square root of 1 minus r squared over the square root of n times s dy over s dx. And these cancel out, and then you simplify that, and that's where that comes from. You'd get, that's where this comes from. You'd get r over the square root of 1 minus r squared times the square root of n. And you just do n minus 2 for t. So, but it's easier to remember, but what I would do is, you're going to see over and over and over again this statistic. So what I would do is note the z and t formulas are the same as the square root of these. So if you remember r squared over 1 minus r squared times n, then just take the square root of that. Z, for simple regression, is equal to the square root of chi squared. So you just take that and you get that. And same here. And t is equal to the square root of f. For simple regression, that's when p is equal to 2 only. Okay? Otherwise, we have to adjust everything for the other variables in the model, the other x's in the model. Now, this is all for regression, but probably if you've started by the end of the, after we hit chapter 29, you saw it all applied to means as well. So, I said in multiple regression, but let's make sure that you know, because it's much easier to remember it this way, that this is for multiple regression, and this whole thing is the same for testing, the same thing, H naught, what? That all group, instead of all slopes are equal to 0, all group means are the same. All group means are the same. And the only thing that's different in comparing means. So this is for regression, and this is for comparing means. They're going to be exactly the same. So what would it be? So you'd have chi squared. Instead of p minus 1, you have g minus 1. Number of groups minus 1 is equal to r squared over 1 minus r squared times n. And then you can do f, and instead of having p minus 1, it's g minus 1 and n minus g. And it's the exact same thing. It's r squared over 1 minus r squared times what? n minus g over g minus 1. So it's exactly the same. And the number of parameters is equal to p, which is equal to g for means. Everything else is the same. P is equal to g. All right? Any questions on that? What I'm saying is you just have one formula to remember. And just if you're dealing with, we can do an example right away, it's exactly what I said here. It's this. See? For regression, P is equal to the number of betas in the regression equation. For means, it's the number of parameters is equal to the number of groups. So it's the same thing right here. Okay? So maybe that's where you should have written that you just have chi-squared is equal to r over 1 minus r squared over 1 minus r squared times n. It's the same exact thing. It's just either p minus 1 or now it's g minus 1. It's the same exact statistic. And for f, it's the same exact statistic, except what do? You replace the p with the g. Any questions on that? Okay. Now, let's see what else we have to do here. So why don't we just jump ahead and do our first example in the study guide, or would you like me to do, since this is already worked out, why don't we do one in the practice exam? So I've printed out some practice problems, because you already have all this worked out. Yes?
I have a question for the practice exam.
From the practice exam or the study guide?
For the practice.
Sure. From the practice exam. What page? What problem?
It's chapter 30 through 31, binary variables.
Okay, can we just do this first and then I'll get to that next? Remind me right after. Okay? Because we're going to go on after, because this just ties together what we just did. All right, so let's see which one I wanted to do. Okay, so we can do this one right here. All right, so you will have to do something similar where you're given the actual numbers, right? The actual numbers. So this refers to what? This refers to this formula right here on page 105. Okay, that. And that's, let's look at this. So the SST is given to you in the table below. So where is it? It's right here. Okay, the SST is given in the table below. And now, this is a different example. Sorry. How did I print out a different one that I worked out? Hold up. Let me see if I have another. I guess I can work it out. I just haven't done it yet. Why don't I do the one so I'm sure not to make any mistakes and you don't have to watch me go through all the arithmetic? Why don't I give you the one I've already done? So let's look at this together. Okay, so here's the one that I've already done, and it will go faster. All right, so now it's because these problems change every time you print them out. So this is good practice for you that it changes. So you can do it with different numbers. All right, so now you're given this, right? And the sum of squares between, how do you figure that out? Well, it's your predicted for each of your points. So you have 9 points here. You're going to get a predicted based on the group mean right here. So that would be 2 for this group, 3, 5 for the next group, and 8 for the third group. Do you see that? And then what you want to subtract off is this overall mean of 5. So you want to see how far away these group means are from their overall mean, okay? So now the mistake that everybody makes is because you've only seen 3 numbers in each group, don't just automatically multiply by 3 because on your exam there might be different number of numbers in each group. Okay? So let's say it's for each one of these numbers. There's, you're getting this difference of 3 squared, of 9. So that's why if there were 4 numbers in here, each one of these would be 4. You're doing it. Does that make sense to you? So don't just automatically put a 3 in there. If there are 10 numbers in each group, that would be 10, because for each number, you're predicting, you're saying that, you're making a prediction saying that, let's say in this group, we're saying we're predicting, because they're in this group, our best prediction is that their mean is 2 for each one of these numbers, and then we're just saying how far off that is from the overall. Does that make sense? Okay, so I did that and I got a 54, okay? So once I did that, I could fill in this chart here. I don't have to use this, I could fill that in. I say 204 minus 54 is 150. Does that make sense? Because they have to add up. Now here's where I get the degrees of freedom. N is 9 and the number of groups is 3. Okay? And then, how do I get these mean squares? It's the way we always do it. This is the same structure as for regression. It's exactly the same thing. 54 divided by 2 is 27, and 50 divided by 6 is 25. And that's how you get the F statistic, is the mean square between over the mean square within. It's exactly the same as in regression. All right? Now, how did I get this r squared here? It's not given to you. How do I get the r squared? How did I get that? Well, remember, this is why I wrote this r squared. Remember, this is your SST, and we're dividing it up, and the model is r squared times SST, and the error is 1 minus r squared. So you'll just say r squared times SST is equal to the sum of squares between. So I'm just solving now for r squared. So, yeah. So it's this relation. Sum of squares, the fraction of the sum of squares model over the sum of squares total. So what I'm saying is you can do this whole thing by r squared. And I just want to show you it's exactly the same thing you do with regression. Because what happened is we were presented, I said this is chapter 21, and we only went this far. You can calculate the sum of squares within 2. That means you take each number and you subtract off its prediction. It's the observed minus the predicted. So you do it for each one. And you should get 50 if you want to check it. But you don't have to. Once you have one of them and know the total, you're fine. So I just wanted, the reason we didn't do this in chapter 21 was because you hadn't had regression, you didn't know what a correlation coefficient was, nothing. So you only went this far, but now that you know it all, it's so much easier just to remember this as just a special case of regression. That's all you're doing. This comparing means is just like what you do for regression. You just have the number of groups is your number of parameters, and everything else is the same. Okay? You got it? Any questions on that? Now, so let's see what else. I'm just going through here. All right. So the scatter plot below, well, came out on 2 pages. Anyway, what does this show? GPA and the number of med school apps filed by med school applicants. Okay. And this is a combined plot for males. Oh, God, blue and females red, ignoring gender. Well, you can't see the blue and the red. But you can when you go to your, you can see it there. Okay? So that's it. Now, here, you've got the apps for, now what's this? All right, so there's 2 lines here, parallel, because what's going on here? They have the same slope, so we're forcing them to have the same slope, no interaction term here. See, what would be the interaction term? It would be GPA times gender. We don't have it here. So we have two different ones. And now, well, there's simple regression. This is for males and females. And they force them to parallel. And here, this is how they really look. They really have different slopes. What does that mean? The ones for females, I'm just curious. For females, it looks like this. The higher their GPA, the fewer applications they make. Well, that makes sense. But for males, it doesn't seem to make a difference. Okay. Now, what are we supposed to do? We're supposed to include the binary variable gender in the multiple regression equation and make it equivalent. See, there's no interaction term here. See? This is plus GPA plus something, so this just includes gender here. So we have apps equals an intercept, B naught, plus B1 times X1 GPA plus B2 times X2, which is gender, right? So no interaction. All right, now why does this one look different? This one says apps, or Y, as well be consistent here, what we're predicting. And this one, you see it has this term right here. This is your interaction term. Gender times GPA. That's X1 times X2. So we have Y equals beta naught plus beta 1 X1 plus beta 2 X2. And then we have this other interaction term. I'll say beta 1, I'll say beta 1, 2. It's a different thing. Times X1, X2. All right, so that we have to do that. Now, do you want to know how to fill these blanks in? All right, so right here, you want to fill this in for what? Gender equals 0. When gender equals 0, let's just put that in. For gender equals 0, and I think it's males are coded as 0. In this case, so this will match the male equation. Does that make sense? Let's see if it did. Yes, right there, because we said males are equal to 0. That's really important. Okay? So now we've got that. Now we want to make it, and this is the female equation. What's different? Their slopes are the same. See, slopes are the same. We just want to adjust the intercept. So what do we want to do? We want to add 0.42 to it. So we go back here. This is going to say, now when females are equal to 1, females are equal to 1, this says times gender. It's so hard to read. So that becomes 1. So we want to add the 0.42 to make this. You see, that will adjust the intercept. Does that make sense to you? Does everybody understand? All right. That's a simple one, because this slope is the same for both of them. Now, the next one's harder. Okay, but we're going to do the same thing. Here, right here, we're going to do this part. This, the intercept. Let's look at the two equations. Here we go. What's the difference? Now they have different slopes and different intercepts, right? So you want this part right here, the intercept and the GPA, to be adjusted for males, because they're coded as 0 for gender. So just copy that down in here. You did. All right. Now, to get the GPA, what do we want to do? Times GPA, this says times gender here. So now when females come into this is gender, this one becomes 1, right? And this also becomes 1. So you see how GPA is going to, this variable is going to change the slope. It's going to add something to the slope, and this is going to adjust the intercept. So how did I figure that out? What did I wanted 35.3 for the intercept, didn't I? 35.3. I want to change that 7.05 to 35.3. So I just put 35.3 down. That's what I want to change it to. When I put a 1 in there, that would be, there's no variable then. It's just your intercept. But I already have the 7.005, so I want to subtract it. So I didn't even do the math out, but that's what it's going to be. Then I'll end up with 35.3. Same here. When I put a 1 in for gender, the gender is going to disappear, and this is going to be the difference, what I want to get. Okay, apparently I want negative 7.39. Let's see if that's true. Yes, this is what I want my equation to be. So I put that in, say, okay, but now I have to subtract off that part. I mean, I already have that much, so I want to subtract it out. And then when gender is equal to 1, I'll get this. This whole, yeah, that's good. Isn't that right? Does that make sense? All right. And which plot gives exactly the same? Well, if there really is an interaction, so they're just about all, the one that adds the interaction term gives exactly the same thing. Does that? Because there was different slopes. Good question. Anybody else want to see anything else worked out in the binary? So you know how to do those binary problems, basic? Okay, great. Oh, let's see. So let's make sure we didn't skip anything. So now let's see. So I think this is just more, there's a ton, here, Bonferroni correction. We didn't go over that, and how to do pairwise comparisons. So let's look at this one, question 3. So it says last semester, so students reported how many drinks they typically consumed and what religion they were. So, we're doing an overall test to see if these groups, differences, are significant or not. So how do I know which is the F and which is the chi-square here? Well, what do I do? 25.37 versus, sorry, it's all cut up. You can't even see it, versus 3.590. Well, the smaller one's going to be the F, right? Because if I actually did it out, I have to divide by 7 to get it, It's r squared over 1 minus r squared times, it gives you the degrees of freedom. 7 is, and this is given to you from the previous page. Everything's given, so it's a pretty easy problem. You could have looked at the p-value. Which has a smaller p-value? Chi-squared. So we could compare 0.08 to 0.06. There's many clues. Look, it has 2 sets of degrees of freedom here. There's a lot of different things you could compare. So, anyways, we did that. And as you can see, both are significant, so you can conclude at least one of the pairwise, at least one of the groups is different. Which one? So what I did is I saw the largest pairwise differences between Jewish and Buddhist. So they have small sample sizes, though. But look at their averages. It's 9.186. Who's drinking so much? Which one? 10.89 versus 1. I don't know if that's unusual. Anyway, I'm looking at this difference here. That is a big difference. But remember, they're small sample sizes. So it might not be the most significant, all right? Because these sample sizes are very small, so they could change. All right, but that is, can we conclude these differences? No. If a large difference comes from groups with significantly smaller sample size, the difference may not be significant. We're going on to the next one. This is so hard to read. The second largest pair comparison is between the Christians, and there's 493 of them, and the Buddhists, 27. Now we've got this big sample size here, at least. So compute the t statistic. First of all, so what are we going to do here? So our t is just going to take that observed difference between the two of them. It's going to be your observed difference, always minus your expected difference. This is not surprising. You always have it, and that's 0, over the standard error for the difference. And this is what you're going to have to remember, but there'll be hints within it'll be multiple choice. So what is the standard error for the difference? So it says right here to use this. Well, the standard error for the difference is going to be your SD plus errors, if we're doing the t-test, and that's given to you. And then it's the same one, it's used for both of them, times 1 over plus 1 over the sample size for one of the groups, plus 1 over the sample size for the other. Okay? We always divide by the sample sizes here, but we're using the same for both of them. So we took that out, factored that out, and that's what we have. So in this case, if we wanted to compute it, we just take, it's given to us, the 9.6, and we just say 1 over 493 plus 1 over 27. And that's going to be multiple choice. Okay? I did this, and I got 1.9 as my answer. Okay, so that's the standard error. Now, how do you get your t-statistic? So your t would then just be your observed difference here between the two group means. And so what are the two group means? We just looked at them. So you just take their two means, and it's that. 7.8, you just subtract them. I think it was already given to you, wasn't it? Yeah. So you just, there's the difference. So it's just 6.17, and you would divide it by the 1.9. Okay? It's going to be multiple choice. It's much easier because you'll be able to identify it easier. And if you make a careless mistake, it probably won't be there on the... How many degrees of freedom? That's n minus the number of groups. So there's 8 groups here, so that was 850. And so you use the degrees of freedom for the whole sample, not just your particular group size. And the p-value is that. Okay, so you're given the p-value. How does the Bonferroni correction change that? It multiplies it. Remember, the Bonferroni will multiply it by what? The number of pairwise comparisons. So in this case, you have 8 times 7 over 2, 28 comparisons. So you have to multiply that by 28. Okay? Does that make sense? All right. The next problem, we're starting here. The next problem is very similar, and it's more like probably what you'll see. It's just the structure of it. So that's a good one to do. Question 4. Make sure you know how to do that one. And here, again, if you don't have the r squared, but you have these two, the sum of squares for the model and the total, there you can just say r squared is sum of squares for the model, or for between, over sum of squares total. And sum of squares model over sum of squares total, same thing. So you could put that in there. And now I think this one, does anybody have any questions on correlation, simple correlation? Anybody have any question on one like this? Okay, I'll let you do this one on your own then. Let's look at the next one. I think these are good to think about here. Do you want me to go over these or not?
Yes.
Okay. Okay, as x increases, all right, y usually decreases. So think of this, as x goes up, y goes down. So you're going to get a negative correlation, but it's usually decreases. Even if it was always decreases, you don't know how much it decreases by. So what were our options? Choose the closest answer, the best. So what's it going to be? You're going to have a negative correlation. Probably it will be between 0 and negative, it's going to be some negative correlation, but it's not perfect. Right? Okay. Now, as x increases, so this would be the positive correlation, but not perfect. It slopes up. Now, if they're random numbers, then it's just no correlation. Here's x and here's y, no correlation, right? So r equals 0, no correlation. Y is always larger than x. If y is always larger than x, all it means, let's see, we can just deal in the positive quadrant. We don't have to go negative. Y is always larger than x. Okay. Here's the line x equals y. Y equals x. So if y is always larger, wouldn't it just be up here, but you don't know what shape it is. So you don't know anything. Right? You have no idea if it goes this way, this way. Look, you're larger than your pet, probably, unless you have a tiger or something, right? You're larger, but is there any correlation? You tell me how am I supposed to know how, do bigger people have bigger pets? Or there's not necessarily any correlation, right? So there's no correlation. Y is always 5 more than x. That's a formula. Y equals x plus 5. If I tell you what x is, you know what y is, and it's a line. So that's a perfect r equals 1. X plus y equals 10. So that's the same as saying y equals negative x plus 10. That's a perfect negative correlation. I tell you what x is, you know what y is, and it's a line. Right? So that's r equals negative 1. All right, so we did those. Now, moving on. Prediction error. This is about outliers. In a data set that contained heights and weights, one student was very tall and skinny. Heights and weight. So it goes like height and weight. Tall and skinny would be, his prediction error was huge. So if this was height and this was weight, he was like out here. I decided to remove it. Before I removed the point, it was 0.4. Correlation was 0.4. And then after I removed it, okay, this is kind of hard to see, but after you, see how this, we're fitting, okay, so most of the points, he's extremely tall and skinny. I've got him in the wrong, oh yeah, that's right. His weight, what am I predicting? I'm going to predict height. Doesn't tell you which is which, but let's say I did height. If he's very tall and skinny, he's way down there, right? His height's high and it's there. And most of them are here. Okay, now this is pulling this, if I have it in here, it's pulling this down. It's like a seesaw, it's pulling this down. So when I let go of it, it's going to go up more. So R would increase. Does that make sense? In general, if you have these points, they're going to, if they're at the end of, at the either end, they're going to have a lot of influence. In the middle, they're not going to have as much influence. But in general, removing an outlier will change the correlation. You don't know if it's going to go up or down in absolute value, but it will change it. I mean, sometimes it could make it, removing it could make it go down. But that's an outlier. So it's going to be like that, but if I remove it, the correlation will go down. So you just don't know. You'd have to see the picture, but you know that it changes it. Does that make sense? Mm-hmm. Yes.
So what if the outlier was he was really tall and he was really short and then weighted so it was the opposite of that?
But don't worry about it now, okay? Just no changes, all right? Okay. I mean, it's kind of, sometimes it's hard to tell. I'm not going to give you one that's hard to tell, okay? All right. I know we have to get moving on. Now, okay, you're going to see something like this, and you have 2 lines. Which one is the regression? Always the flatter one, okay? That's the standard deviation. Now, how would you figure out from this what the correlation coefficient is? That's on the next page. Well, you can draw this right triangle anywhere you want, starting at the point of averages where the 2 cross and just going horizontally out. because this can give you a measure of the comparison of the slopes. You have the same, you're going, rise over run. You have the same run, and you're comparing these two slopes, which is what gives you the correlation. Remember? Okay, so this flat one, r is equal to 0. If somebody's on the standard deviation line, let's just say it's 100, let's just say, then you have a correlation up here of 1. So you're just measuring how far up it is. You can go between 0 and 1. So you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, something like that. That to me looks like around 0.4, because it's about 4/10 of the way up. What are our choices? Yeah, 0.45. So that's the, 0.9 would have to be really close. This regression line would have to be almost like way up there. Does that make sense? It would have to be very close. Okay? All right, let's go. What happens to R if we remove Delaware? Well, there we go again, another one of these. Delaware. Okay, here we go. Delaware is making this end go up a little bit. So if we remove it, it's a big error, and it's going to get, R is going to go up. Okay, I think the average is where that's the point of averages. You can look on the graph. Poverty rate, which one's poverty? This is the point of averages, where? About 13. Which state has prediction error 0? It'll be the state on the regression line. Which state has z-scores the same? That'll be a state on the SD line. And that's how I got those. Okay? Questions? If it has a prediction error of 0, Wyoming, if that's Wyoming, we made a perfect prediction. Which one's Nebraska? If Nebraska's on the SD line, that means it's exactly the same z-score in X and Y. All right, let's move on. Now, okay, so you're going to have to find the regression equation. You need to know how to do that. And then to make a prediction, you start with the slope, r times s dy over s dx. I'm not going to do it all for you. And then to get the intercept, you plug in the point of averages. Does everybody know how to do that? I don't have to do that, right? Okay. And then you can make predictions. Residual is the actual minus the predicted. Standard deviation of the errors is just the square root of 1 minus r squared times the standard deviation of y. Be careful. You have to know which one you're predicting. In this case, weight is y. Okay? How would you get this? All right. Instead, there's a range with about 85% of them falling within how many standard deviations? You just look on the normal curve for 85% in the middle. And then whatever z-score that is. I don't have a z-score, normal curve. 85 in the middle, 1.45. So that would be your answer. All right, let's look at another one. Let's see what else there is. All right, well, here I did this, the slope for, 95% confidence interval. Okay, so remember, the confidence interval is the sample slope. If we're doing, if I don't tell you otherwise, here we're just using z. I should have said using z, using the normal curve. I'm sorry I didn't, but I assume that's what it is. So you'd say, or maybe it's not. Didn't I tell you here? Yeah, this z statistic. Okay. So how do you get this? All right, the sample slope is this. And how do I get that too? If you're using the normal curve, I went like this, and I know that 95% is in the middle. and I estimated between 2 and negative 2. You could have used 1.96 as well. Now, how did I get this right there? That's the standard error of the slope. I had to go to my formula page. That's going to be given to you. It's the square root. It will be on the front of your exam. Square root of 1 minus r squared times, it's just, do you understand how to do that? It's the formula. It's just the formula you're going to be given right here. It's the standard error of the slope. And I promised I would give that to you. So it's this one right here. That's what I'm using. Okay, so if you don't know how to do it, just look here. And I just plugged in the numbers, okay? Then, to test against the alternative, we compute a z-statistic. So how did I do that z-statistic? There's a lot of ways you can do it, but I think the easiest way is just to use this, r over the square root. You could do r squared and take the square root of it. Or, since you already have the slope you computed and your standard error, you could do this. So here's 3 ways to do it. Okay? Just whichever one's easiest for you. You're given r and n, so I think this is easy. And this is all you can remember. Take its square root. Okay? Questions? Remember, this is not given to you, but this one is. So you could always derive it, or you could just remember this one and take the square root. Okay? Now, if you square the z, you get the chi-squared, and if you square the t, you get the f. This is only for one slope. This is when you just have one slope. Okay, suppose the p-value for the hypothesis test in part C, so you have to see what that alternative is. It's two-sided in part C. That's two-sided. There's no direction, not equal to 0. One-sided would be greater than 0 or less than 0. Which yields a p-value equal to that. Then your chi-squared and z are going to yield the same. It's the same because it's two-sided. If it was one-sided, the chi-square is always two-sided. So the p-value is the same. That is the same as the chi-square because the chi-squared is always positive. If you'd just been given a one-sided, then your chi-squared would be twice as big because it's two-sided. All right. And the t-test would yield a p-value greater than your z because it has fatter tails. And just p is the area of the tail. Oops, this is terrible. It doesn't matter. She wasn't anonymous. So it doesn't make any difference. Okay. Now, it's a good question, and we answered it. All right. Now, this one, this is, I think you know how to do this one, right? Why don't we skip this one? Because I think people know how to do it. It's pretty simple. It's just the 3 points for the sum of squares. Well, you can look at the formula. Let's move on. What about this one? Okay. Here I gave you the same thing that's on the front of your. This is all the same stuff, right? Oh, here's a good one. Assume in part C that a 95% confidence interval for beta 1 does include 0. Okay? So for part C, right there. Assume that say I didn't want to give away the answer. Here, does it, so I just said assume. It does include 0, because if you subtract off that, it would. Doesn't. Based only on that information, you could conclude a t-test would what? If it includes 0, it would not reject the null. It would not reject that null against a two-sided with 95% confidence interval at 5%. It's just 100 minus 95. Okay? Does that make sense? All right. Now, all right, so here, we're doing the usual, you were given R is 0.4. So we're just computing, I just asked you to compute R squared and 1 minus R squared. And then you can compute the 4 test statistics. I think it's easiest to start here with the chi-squared, R squared over 1 minus R squared times n, and then square root it. And here I said R squared over 1 minus R squared for the F times n minus 2 over p minus 1, which is just 1. And then I square rooted it to get the t. This is your F. Okay, any questions on that? And now, what's this? Compute the p-values. Oh, here assume they're one-sided. So I got 1.75, so that is 4% in each tail, and if it's one-sided, the p-value is 4. But then I'd have to multiply it by 2, because a chi-squared's always two-sided, right? How many degrees of freedom? 1. That's why I can, with 1 degree of freedom, just one slope, chi-squared is z-squared. And then this one was harder to do. I had to look on a table. I know it's greater than 4%, because I'm comparing it. It's going to have a fatter tail. You'd have to use a calculator. And then 2 times the p-value for the t. Okay? And you'd get p minus 1 again here, which is 2 minus 1, which is 1, and n minus 2. All right, let's see what else we need to do here. We already did this one. Thank you for your question. Let's go on to this one on page, this is question 14. There's a good one to look at. So this pertains to these 2 scatter plots. Okay, now which group has a negative relation between x and y? Which one? This is positive, positive, it's group D. For which scatter plot is there an overall negative relation? Well, there's one here, even though there's positives here. For each, that's confounded, there's a negative. So it's group plot 1 only. Where is there an interaction? That's different group slopes. No interaction here. Here's an interaction. Plot 2 only. And the last question says, for which plot does there appear to be confounding? So remember, you have to have different x averages, that one does, and a different overall slope than the group average. Here's their overall, and this would be the average of the 2 groups, like right the same. Different x averages, and here the average of a negative and slightly positive would be kind of like, it would be something negative and it's about equally positive. It would be something like, it would be flat, but this is different. So there's confounding in both. So the overall is not equal to the average. The overall slope is not equal to the average of the 2 group slopes. And they have different x's too, those 2 conditions. Any questions on that? Okay, I think you know how to do those. All right, now what do we have here? These are more binary. Where is it leading? Let's just go to something that we did today, because this is more binary. What is this? This is a correlation matrix that you have to figure. This is a good problem to do. And here's another good problem to do. Well, we can look at this one. This is 16. I want you to fill in the blanks of the correlation matrix. Well, the diagonal is going to be 1 because it's just a variable with itself, and these are going to match because it's violent, So this will be the same. And these 2 will match. Now, the slope for predicting a simple murder rate from violent crime, that's just going to be the correlation between, where is that correlation? Between murder and crime. Murder and crime, it's this one right here, times the two ratio of their standard deviations. This is so hard to see. Oh my goodness, you can't even see this one. Maybe I should do this one, because you can't even look at that. You don't have a copy of it. I'm so sorry. All right? So let's do this one. It's sort of the same. All right? So now you have to fill in these. The blank for this one is going to be what? 1. So that will be 1. And the blank for B will be what? 0.17. Students A and B study the same number of hours but differ by 6 points. So how would you figure out how many? Okay, 6 points in their GPA. Okay, in their ACT. So they differ by 6 points in their ACT. So how many are they going to differ by in their GPA? Well, 0.03 times 6 is 0.18. So the difference is going to be that, the difference between them. Does that make sense to people? Okay, let's see. The slope for ACT in the multiple regression is that. The ACT in the simple is going to be greater because remember the multiple regression is a partial slope, explaining the effect after the other variables have been partialed out. If they're all positively correlated, it's going to, which they all have positive correlation, it's going to be greater in the simple. How is this calculated? Very important. It's a correlation between predicted and actual. All right. Now we're going to just do chi-squared and F tests for these. You're given N and R, and then what are we going to do? Getting p-values. This you're going to skip. This comes next. Don't even think about it. Ignore it. And what else do we have? Now, if you decide to reject the null, you know either one, at least one of the slopes is significant, or both. To see which, we ran a Z and a T test. Which table shows the T test? This one's pretty easy. The T test is going to have what? T test, T p-value will be greater than Z p-value. That's an easy one. So this is it. You can see this is the, also it's going to have a bigger slope. So this is the T. And I just want to show you that, where's the R squared problem? Does R squared go up or down? It must be in, if you add a variable, R squared goes up. Let's see if I can zoom in so you can actually see this. Whoa. Whoa. And this is going to be the same. It's not randomized. So let's see. All right, let's read it together. Here's the multiple regression. Compare the slope for violent crime in the multiple to the slope in the simple. Why did the slope go down in the multiple? It's because they're all positively correlated with each other. So it's going to, we talked about this a lot. It's going to go down in the multiple regression. It'll be stronger in the simple. Now, where's the R? I guess I don't have it. Oh, it's in your homework. The R squared will always go up or stay the same every time you add a variable to a model. All right, I think that's it. And so anybody have any questions? I think we covered everything. Yes, I'm sorry I didn't answer before. Go ahead.
No, you're good. Are we going to have a multiple regression leading into a simple regression?
Are we going to have I'm going to repeat so everybody can hear. Are we going to have a multiple regression that's what?
That we simplified with a simple regression because it was on the notes and you said there might be an exam problem on it.
Oh, where you have to, from the multiple regression, get the slope from the simple, like that complicated? What? Let me see. actually calculate it, go backwards and calculate?
Yeah.
No.
Okay.
We were not going to have an example where you have to go backwards from the multiple regression and calculate the simple one in that way. Any other questions? All right, well, good luck, and there's office hours today from 3:30 to 5:30, so come by in third floor, 703 South Wright if you have a question. Bye. Hey, thanks for asking those. That's good. The office hours are